Have any of you had power issues? One of my students lost power. That might be a very localized thing. Are any of you having that issue? No. In this area, it doesn't take much for a branch to touch a power line and you're in trouble. Okay, let's get started. Last time we found what was called the fundamental theorem of calculus. It's essentially the shortcut method that allows us to get the integral, the area under a curve. So from x equals a to x equals b or some function. And the fundamental theorem of calculus part 2 says that this area could be found by finding the value of the antiderivative at b, subtract the value of the antiderivative at a. And that's very, very useful. And we spoke a little bit about antiderivatives because we'll obviously need to find those guys. And what I've got here is a list of some of the basic ones and a few extras that I haven't got to yet. And this piece of paper is a PDF in Canvas. So if you want to print it for your own benefit later on, you feel free to do so. And essentially, we have a power rule. This bunch of questions essentially involves all the trick antiderivatives that are simple to find. And there's my favorite e to the x. The antiderivative of 1 over x is log x, and a few others that we won't need today, but we will need eventually. So we are going to be using this property to do with antiderivatives to find the area under a curve. We're going to spend a lot of time today on one particular version of that list, and that's called the power rule. And what the power rule allows us to do is to essentially find the antiderivative of any power of x. So 5x cubed, 7x to the half, anything like that. And in English, which is the way I tend to remember it, is you would add 1 to the power, and then you would divide by the new power and put a little plus c on it. So we are going to look at using the power rule to find areas under curves. I'm going to stop calling them areas under curves, which is a bit of a mouthful, and I'm just going to call them integrals. So let's look at our first integral. The integral from 1 to 2 of 3x squared plus 6x minus 2. So we are going to worry, or not worry, but we're going to look at how do you find integrals of polynomials, right? X cubes, x squareds, that kind of stuff. So that's my first little subfamily of things to do. Well, the antiderivative is add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. Now, when you have numbers, we call them constants, like -2 or +5. The rule is essentially, it's a special case, just give it an x. So +5, its antiderivative is 5x. -2, its antiderivative is -2x. Now, if you want to see why that works, I just remember that constants become constant with an x. And this is essentially why it works. It is a power rule. -2 can be thought of rather artificially as -2x to the 0, because x to the 0 is just the number 1, right? So -2 times 1. Now you do the power rule, which says add 1 to the power and divide by the new power. Well, -2 over -1 is still -2, and x to the 1 is called x. So do you see how this number has that as its antiderivative? And so it's a lot easier just to remember it as a special case than to do all this weird artificial thing in the middle, right? So constants, plus 7, minus 3 halves, plus 42, doesn't matter what it is. They are all, you can get their antiderivatives of all of those by just sticking an x at the end, as we have here. So this is the antiderivative of this polynomial. And the usual convention is you then just do a vertical line and you put in the start and finish value. So when we plug into essentially finding this guy, we're going to get 2 cubed plus 3 lots of 2 squared, take away 2 lots of 2, subtract 1 cubed plus 3 lots of 1 squared, take away 2 lots of 1. That guy is 8. That guy is 12. That guy is take away 4. And that's 1. And that's add 3. And that's take away 2. So we get, what do we get? We get 16. Take away 2. And so in this case, the answer is 14. So,
I have a question.
yes.
Why don't we add the plus c when we do the x to the third plus 3x squared minus 2x plus c?
Okay,
Why
let's
don't we do that?
yeah, let's put it in. Let's put a plus c then. So this guy is going to have a plus c, right? And so will this guy, right? So far, so good. Right. So if I give them the plus c, right? So this has a plus c and this is plus c. I'm going to have a plus c here. I'm going to have a plus c here. And I'm going to have this guy take away that guy. And that's going to be 16 add c, take away a 2, take away a c. Do you see that the c's will always cancel each other out? And it really doesn't matter what antiderivative calculation you're doing. The plus c's are not necessary when you are doing definite integrals. That means integrals with numbers here and here. The only time they become much more important is that if you don't have an integral start and finish number, right? And when that happens, we call those guys indefinite integrals. Then you do need the plus c. Have I convinced you that you don't need the plus c only because they always kill each other off and they don't appear in the final answer? So if you know they're always going to kill each other off, you can save a bit of time by not writing them down. We're cool on that?
Thank you.
Okay. Now, polynomials, check. How about the integral from 0 to 2 of 2x plus 1 squared? Well, that is a polynomial. It's just not written in a way that I can use the power rule. I can only use the power rule when we have individual powers of x, and that does not have it. It's a calculation. So what I need to do here is I need to rewrite this fella as 2x plus 1 times itself. Foil this whole thing out, and you will get 4x squared, plus 4x, add 1. So I cannot use the power rule on this, but I can use the power rule on this second one. That's interesting. Ginger was saying the book goes on and says that you can use any number for C that you like. So why don't we just make it 0? And that's her way of, makes sense, of why that's not important. We could say plus 0, because it wouldn't matter. Now, that is impossible to do as a power rule. This is add 1 to the power, divide by the new power. Add 1 to the power, divide by the new power. The number 1 gets you x. Plug in 2. So we have 4/3 times 2 cubed. Oh, looks like I have someone else in the chat. Gotcha. So 4/3 2 cubed, 2 lots of 2 squared, plus a 2, take away. And you always want to try and do things efficiently. Technically, I should be writing here 4/3 times 0 cubed plus 2 times 0 squared plus a 0. But as you can see, all you get is a whole load of zeros. So if you know, because you can see the calculation in your head, that you're not going to get anything worth writing down, right? This is 0 plus this is 0 plus this is 0. You can just say take away 0 and save some time. Now 248 gets me 32/3, 248 plus 2. Now, when we are dealing with integrals, areas under curves, we have to have exact values. So I'm not going to try and turn that into, or whatever it is, 20 and 2/3. It needs to be a single fraction, not a mixed fraction. And so the easiest way to do that is actually to use your calculator. And so I'm going to show you, if you didn't already know, how to do that plus that plus that on a calculator and get a fraction as our answer, which is what we want. So right now you're looking at this guy, okay? So the calculation was, and you can use your TI-84 to do fractions, is 32/3, add an 8, and add a 2. Now when I hit enter, a decimal is going to appear, and that's okay. But that's not the answer. You cannot write into WebAssign 20.666 because you are not writing the exact value, because you would have to round that decimal off at some point, and then it stops being exact. So this answer is going to be turned into a fraction, and that will be the exact value. So hit the math button, choice number 1, which is fractions. And the answer is going to be turned into a fraction. So press enter, and 62/3 is the answer. So if you're doing, as you will probably be doing in some of these questions, 7/13 plus 5 minus 3/4, right? Weird fractions being added and subtracted. And you want a single fraction as an answer, this is the way to do it, right? Use your TI-84, it'll do the whole heavy lifting part for you. Just kind of nice. Now, still working on polynomials, or at least working on powers of x. Here's my little list to keep going. Let's look at the integral from 1 to 2, and let's look at simple fractions like that one. Now, right now, that does not look like it's a power rule, because it's a fraction and it's not 10x cubed, it's 10 over x cubed. It is a rational, it's a fraction. What you need to do is you need to be aware that there are some tricks in algebra where an x cubed in the bottom can be rewritten as a negative power. Now, the power rule actually doesn't care if the power is a positive number like x cubed. Or for that matter, a negative number like x to the -2, it doesn't matter. So the power rule says add 1 to the power. No, it's not -4. If you add 1 to -3, you get -2. You then divide by that new power, which is where this guy comes from. So what I've just written down here is the antiderivative of this guy, which originally looked like this guy. And now we bring into play what I call style points. Your answer to your antiderivative can't just be left in whatever weird form it ends up being. There are rules about how it should be written. And the two major rules are going to be, number one, make it look like the original. And number two is simplify if possible. But rule number one, this guy and this guy don't look the same. So I'm going to rewrite it like that. And now he looks the same as the original. And that's important, not just because it looks pretty, it helps later on when you put in numbers. So what we're going to do here is -5 over 2 squared, take away, that's the first guy, take away -5 over 1 squared. So that's what, -5 quarters, and that's -5, two negatives make a plus, and you get that. And I believe the final answer ends up being 15 quarters. And so in this format, the answer comes out really nicely. If you had left it in this format, you would be doing calculations like this. And good luck trying to make that look pretty, right? Negative powers doesn't look good. Turn them into the same format as the original, it comes out much cleaner. How about this situation then? Just keep that there for a minute. I would like to know the integral of 4 times the square root of x dx. And I am still on power rule. Well, I have to find a way to write the square root of x as a power of x. It's actually going to be a fractional power of x. What is the fractional power of x that the square root of x would become?
1/2.
1/2. Now, once you get to this format, it's a power rule. As weird as it looks, it's still a power rule. I'm going to add 1 to the power. Now I'm going to divide by the new power. Well, dividing by 3/2 is the same thing as multiplying by 2/3. And this fella now becomes 8/3 x to the 3/2, evaluated at 4 and evaluated at 9. So that's where we are right now. And now I'm going to bring into play my style point rule. And my style point rule says that this guy should look more like that guy. And that guy has a square root, so should this guy. So I'm going to write it as 8/3 the square root of x cubed. Are you comfortable with 3/2 being the square root of x cubed? Fractional powers. Right? It's a lot of algebra is taking place today, right? Little things you might not have seen for a year or two, right? Like, you know, fractions become negative powers and, you know, vice versa. Square roots become fractional powers, right? Fractional powers can become square roots, right? Those kind of things. Now, I'm going to plug in our values, and it's going to be 9 cubed, take away 8/3, 4 cubed. And I happen to know that this answer is going to be 3 3 3s, that's 27. So 8/3 times 27, take away 8/3 times 8. And at this point, I'm going to let the calculator take over. So you're just going to hang in here for a minute. So I'm going to go 8 times, oh, I just noticed they cancelled down. Okay, 8 times 9. Should always make your answers, you know, the easiest to work with, right? That cancels. So what have I got? Really, I've only got 72. Take away 64/3, which is a lot easier to do in the calculator. And I'm going to do convert to fraction, and you're just going to trust me, it's 152/3. Are we good? Square roots, cube roots. Let's try the next situation. This one's really ugly. I want to use the power rule to find that integral. 6 over the cube root of x. Now, to be able, excuse me, to be able to use the power rule, I have to write this fraction in some way or another in the form of a power of x. I'm going to take it slowly. The cube root of x squared, right? The cube root of x squared can be written as what fractional power of x? The cube root of x squared.
X to the 2/3.
Correct. The root is the bottom, the power is the top, right? Now, this guy, in turn, can be now written as that negative power thing. Remember that negative guy that we did? Right? 2/3 in the bottom, negative 2/3. Excuse me. In this format, we can use a power rule. Now, if you add 1 to negative 2/3, you get positive 1/3. If you divide by that new power, you're essentially multiplying by 3, and you get this guy, and it's going to be x equals 1 to x equals 8. Okay, let's bring into play style points. I do not want to do evaluations with fractional powers. I much prefer to do calculations with square roots, cube roots, things like that. How can I write this x to the 1/3? So it looks more like this guy.
Cube root of x.
Say again? I think you're right, I just didn't catch
The
it.
cube root of x.
Yes. Are you all comfortable with the cube root of x for the third power? Now, at this point, we can now do the cube root of 8 minus 18, the cube root of 1. But the cube root of 8 is a nice number, it's 2. 18 times 2 is 36. And the cube root of 1 is 1, so 18 times 1 is 18. And there's our answer. There is a there are a lot of situations where the power rule can be used to find integral. We've done it with fractional things with square roots. We've done square roots. We've done fractional powers. We have done polynomials. We've done things squared. All of those eventually became the power rule. Let's take it one stage further. I want to find this integral. It's a rather ugly fraction. And we don't like ugly fractions because ugly fractions are hard to integrate. What I want to do is to rewrite this as various powers of x. Well, see how that can be done. One way to tackle this question is to rewrite essentially this fraction as a multiplication. Now, if you multiply this by this, you get 2x. If you multiply this by this, you get -4. And if you multiply this guy by this, you get 2x and -1. And then I noticed that this last term is not going to be a power rule. I need to rewrite it in this format. And I need to do that because of this special case. This power of x, x to -1, doesn't work with the power rule. If you try the power rule on this, you will add 1 to the power, which gets you x to the 0. And then you divide by the new power, and dividing by 0 is a bad idea. So, writing that works. Power rule, natural log of x. So here is the antiderivative evaluated at 1 and 2. 2 squared. Take away 4 lots of 2 plus 2 log 2. Subtract 1 squared, 4 logs of 1, 2 natural log of 1. Okay, that guy's 4. That guy's 8. 2 log 2. You could leave it as 2 log 2. You could turn it into the log of 2 squared, which is 4. It doesn't matter. That guy's 1. That guy's -4. What number is the natural log of 1?
0.
0.
So that means that guy doesn't matter. So if I I'm making a meal of this bit, I'm taking it slow. If I take this, take away this, add this guy, take away 1 and add 4, we pretty much got everything we need. We got 4, take away that one, 4, that's that one. So it looks like the final answer ends up being just 2 terms. So a complex fraction can be turned into a multiplication by a negative power, distribute that negative power throughout all the terms and use the power rules, or if you need to, if the special case arises, a log. Okay, here's another one. Make that 4.
I don't think you added the stuff up correctly in the last
Oh,
one.
that is possible. Where did I go wrong?
How did the 8 cancel out?
You think the 8's not right? Let's check. Is this line here, as far as you can tell, okay?
Like, how did you get rid of the 8? Because you have +4 and a -4, which cancel out as fine.
Oh, well, I have actually a +4 and another +4 because taking away a negative makes it a plus.
Okay.
So they did actually disappear. Right, so these two cancelled out that guy. Yeah, I'm happy. But it's worth checking with me. Okay. Let's throw the cat amongst the pigeons and make it even uglier version of a fraction. Now the one we just finished, that x became an x to -1. In this question here, we are going to turn this ugly fraction into various single powers of x. We're going to call this guy 3x to the 4. This guy's still 2x squared. This guy's still plus 3. What do you think a square root of x on the bottom is going to turn into when I put it as a multiplication here? So what will that become?
-1/2.
Okay. Now distribute. 4 take away a half is not easy. It's 3.5, but we don't call things 3.5. We call them 7/2. Take a half out of that one and you get 1.5. We don't call things 1.5. We call them 3/2. And this guy at the end is just that guy. So this has now become 3 individual powers of x. So add 1 to the power and you get 9/2. Dividing by 9/2 is the same as multiplying by 2/9. So you're going to have 3 times 2/9. That's that one. This one, second one, is going to be add 1 to the power. Dividing by 5/2 is the same as multiplying by 2/5. And this one, you're going to add 1 to the power. And dividing by a half is the same as multiplying by 2, so you get 6 for that one. And this is going to be x equals 1, and this is going to be x equals 4. Now, 3 and 3 cancel. What'd you get? 2/3. X to 9/2. Can't really do much with the middle one. It's going to be 4/5. X to the 5/2. And nothing particularly bad about that last one. And we're here. So this is the simplified versions, at least as far as we've got, of the power rule, right, of the antiderivative. Now I'm going to bring in style points. The question had a square root in it. This guy is now going to be 2/3 the square root of x to the 9. This guy is going to be 4/5 the square root of x to the 5. And this guy is going to be him. Now, if you plug in your various numbers, you're going to get 4 to the power of 9 x plus 4/5 square root of 4 to the power of 5 plus 6 times the square root of 4 minus, and now I'm going to do a little bit of work here to save myself some work at least. The square root of 1 to the 9 is the same thing as the square root of 1, so basically you get 2/3 times 1, you get 2/3. The middle guy gets you 4/5, and the last guy gets you 6. But if you do this guy, you get, what do you get? You get 512. So you get 2/3 times 512. And if you do this guy, you get 2, 4, 8, 16, 32. And if you do this guy, you get 18. And you can take away eventually all those guys. And then much more, I guess I could do 1024 thirds plus 12/5 add 18. Take away 2/3, add 4/5 add 6. And so that's going to be this fella. Again, you do not need anywhere near as many lines as this. Take away each of these. So take away a 2/3 and a 4/5 and a 6. And at this point, I'm going to hit the buttons on the calculator and we'll see what we get. So I have 1024 thirds plus 12/5 plus 18. Take away 2/3. take away 4/5. Take away 6. Ooh, I don't like the looks of that answer. And math 1 and fraction. Whoa, I'm so glad that there is a TI-84 to do this, because I do not think I would like to do that any other way. So 5,314/15ths. And do not be put off by really ugly fractional answers in these questions. As much as we prefer the answer to be 4 and -2, the chances are you're going to get ridiculously ugly fractions, because just the way the numbers work out, right? So that isn't a sign that you've done anything wrong. It's just a sign that the question had an ugly answer. Any questions? Are we good so far? Okay, I am going to nip over now and look at, oh, we got 2 things. Okay, someone noticed something. I'm now happy. Right, so I'm going to go in and let's just talk through some of the homework questions. So are we looking at the homework right now? Is that what you can see in front of you guys? Because I can never be sure
Yes.
what you're seeing. Okay, right. Now, if you're doing question 5, would you agree that is a good to go power rule, nothing to worry about? In question 6, that's a power rule. Isn't that also a power rule? It just happens to have fractions in it. And here is our first sneaky question, almost a trick question. What is the antiderivative of the number e? And I'll tell you what it's not.
E?
It's not.
No.
It's not e. Oh, it's another one, and it's not e to the x.
It's
What is the
EX.
anti? Say it again. Sounded right.
EX.
Yeah, exactly. Yeah. And you might be saying, "Wait a minute, that doesn't look right," but it is right. If that was 5, wouldn't its answer be 5x, right? If that was 20, wouldn't it be 20x? Isn't e just a number, right? In the context of this, it's just a number. If I had said to you pi here, wouldn't the answer have been, I don't know if it will take pi, I'll try. Oh, good. Wouldn't the answer have been pi x? And then you'd evaluate it to x equals 4 and x equals -4, and you'd get 8 pi or something. Now, in this question here, do you see you're going to turn that into x to -half and distribute it, and they give you a choice and you pick the right one? This question is good to go. 2x plus 1/x. Won't this guy get you x squared, and won't this guy get you the log of x? And I'm going to leave this now because I have just seen another sneaky question. And I want to write it down. Let me start by saying I do not need to change any of these terms. They are good to go. Let's take the first one. My favorite thing to integrate, e to the x. 8e to the x is 8e to the x. Nothing to see here, what you'd expect. Now here's the weird one. 5x to the power of e. Now if that had been 5x squared, wouldn't you use a power rule? If it had been 5x to the 7/9, you still would have used the power rule. It's 5x to the e, and you still use the power rule. It's just a little bit less obvious what the answer looks like when you use the power rule. So according to the power rule in English, you add 1 to the power. And then what do? You divide by the new power. Does that make sense? Sometimes things look weird and are right. That looks weird, but it is right. Okay, just looks weird. Now, plug x equals 1 and let's see what we get. 5 over e plus 1 times 1 to the power of e plus 1 plus 8e to the power of 1. And that's plugging in x equals 1. Take away 5e to the thing e plus 1 times 0 to the e plus 1. Add 8e to the 0, right? That's all the x's turned into 0. So as long as we're careful about things, we should be fine. Okay, let's forget about all the distractions and just focus on this one term. What number is 1 to the power of e plus 1?
1.
And so 5e plus 1s times 1 gets you just that guy. E to the power of 1 is typically just written down as e. Forget about all the other distractions. What number is 0 to the power of e plus 1? What number is 0 to the power of e plus 1? It's actually a very simple answer. There's nothing to it.
0.
0. So 5e plus 1 times 0 is still 0. Now, what about e to the power of 0? That is a number as well. What number is e to the power of 0?
1.
So 8 of them gets you 8. So our answer is that guy plus that guy, take away 8. Not the prettiest answer in the world, but it is the answer. I believe that was yours, Tony, wasn't it?
Yeah.
Was it? Right. Were you kind of stuck about what to do about this guy?
Yeah, it just looked weird.
Yeah. Sometimes you can talk yourself out the wrong answer, the right answer, because it just looks weird, right? It looks wrong, and it's not. It just looks wrong. Okay. Let's return. Oh, get somebody in chat. Yes, correct. You're right, Dave. So let's return now and see what other situations might appear. Right, we've just done 10. I don't think anything really is going on with the 11. Would you agree? It's just a power rule. Do what you do. 12 is just a power rule, just fractions. In question 13, wouldn't you call that x to the power of half and then do the power rule? What would you do in question 15? What would be the first piece of algebra you would do in 15 before you start thinking about antiderivatives?
Foil.
Foil it out and then do antiderivatives, right? In question 16, what would you do first before you start thinking about antiderivatives again? In 16, what would you do first?
You make it t to the 1/2.
Yeah, and then distribute it. And then you'd have 8t to the half, take away t to the 3/2, and then you do the power rule. We've already done a version of question 17, but just to remind you, wouldn't you do 6 plus x squared times x to the 9.5 and do your thing? Isn't 18 just another foil? We haven't looked at an example of 20, but we should be able to figure out what to do based on other situations. What horrible thing would you have to do in question 20 before you start thinking of doing antiderivatives? And it is horrible because it's a lot of work what you need to do.
Foil.
Yeah, so when you have to go 2 plus 3 times 2 plus 3, get the answer, and then multiply that by another 2 plus, because 2 plus r, I should say, right? 2 plus r times 2 plus r, get the answer times 2 plus r. Horrible thing to do. In this question here, wouldn't you basically just take the numerator and multiply it by v to the power of -3? Right? Multiply by v to the power of -3. And we've done ones like that. And that's all I want to do on those guys. So let's return. Oh, we got some questions. And someone says, could you show me 13? Yes, okay. Question 13, let me, oh, she changed her mind. Could you show me 14? Okay, I will show you 14. If I kind of kick out and kick in for a second to do 14. First, I'm going to find wherever I put the darn thing. Oh, here we go. In question 14, you're being asked to find the integral of pi upon 2 to 0 of cosine of theta d theta, right? Now, the antiderivative of cosine is sine. So the antiderivative of cosine theta is just sine theta. We're going to evaluate it at this guy to this guy. And this is a bit strange because you should have 0 here and pi upon 2 there, but if they write it that way, we'll use it that way. Which means we're now going to have to do the sine of 0, take away the sine of pi upon 2. And whenever you deal with trig, I've also got this guy in Canvas for you. You need to use a unit circle. So let's see how it goes. The sine of 0 leads me to that point, and the sine is the y coordinate, so the sine of 0 is 0. Pi upon 2 takes me to this guy, 0, 1, and the sine is the y coordinate, which is 1, so the answer is -1. Now, let's do another one of those trig guys if I can find one. Yes, okay. This is question 19. Actually, the last one for today. We have 0 to pi upon 4. We have secant theta tan theta d theta. Now that expression, as ugly as it is actually does have an antiderivative. Before I flip this over and show you, can you tell me what is the antiderivative of secant tan?
Should
Do you
be
have it?
secant squared.
That would be a different answer. So go looking for another one.
Is it cosecant?
Okay, let's show you that one. So it's a
Yeah.
secant. Now, the more you do these, the quicker and the less mistakes you're going to be, right? This guy is online with the exception of these 3 guys. So you might want to print it out and do one of those, I guess you do it in French where you just memorize things, right? You just go and say that guy is the antiderivative, that guy is the antiderivative, and you just do it. They're not that many, right? When you add these, there are about a dozen in total, and it's good to have them. Now, that leads me to the secant of pi upon 4, take away the secant of 0. And now I need to use this fella. Now, if you go to the angle pi upon 4, on the unit circle, you're using that coordinate is how you get your answer. Now, what is the secant equal to? It's 1 over the x coordinate. Now, if you take this guy and you do 1 over him, right? 1 over this guy. It's another way of just saying the reciprocal. So you turn them upside down. So this guy is 2 over root 2. Now the 0 is this one. And if you do the 0 guy, you get the point 1 comma 0. And 1 over the x coordinate is 1 over 1, which is just basically 1. So there is your answer. If you want to make it a little bit prettier, you could rationalize the denominator on this side and you'd get 2 root 2 over 2. The 2's cancel, and so actually it is worth doing. You get a much nicer answer that it's root 2 take away 1. And that's all we have time for today. So last name for attendance, and bye-bye Ginger and everyone else. And I will see you online. I'm pretty sure it's going to be online. I felt a lot better this morning, but I'm kind of not feeling so good anymore. So one more day, weekend, fix this damn thing. I'll be fighting fit. Oh, and Monday is a holiday, isn't it? It's Martin Luther King Day. So I won't see you Monday anyway, even if I did feel better. Okay, so last name and bye-bye.